Hello to all participants of the conference. I am Olha Harkava from National University Yuri Kondratyuk Poltava Polytechnic. I am presenting the report on topic experimental test of the overcolumnate plates of the precast building frame. To date, renewal of the housing stock of Ukraine has become one of the most urgent tasks in the field of construction. This task can be solved by introduction modern precast flat plate frame structural system of buildings. The system is being widely implemented in residential construction of Poltava region. The flat plate of the structural system is arranged on columns and is a simple structure consisting of reinforced concrete plates of the same thickness and shape. This composition of floor components simplifies the process of formwork and production and significantly speeds up the construction of objects. Flat floors are directly connected to columns without the using of protruding members, which provides the opportunity to freely adapt the architectural and planning solution of buildings for any purpose. Design of such structural system of buildings is proposed by using the yield line method. According to this method, design of each plate may be performed separate, taking into account loading and supporting conditions. Overcolumnate plates, position number 2, in composition of floor system are the most loaded because load from middle plate is transferred to intercolumnate plate position 3 and then into overcolumnate plate. Experimental data for such plates are scarce today, and so there is a need to experimentally investigate the overcolumnate plates in order to confirm the developed yield line destructive scheme. For this purpose, 3 full-scale samples of overcolumnate floor plates were used for conducting experimental tests. The plate samples had nominal dimension 3 by 3 meters with thickness 160 millimeters. The heavy concrete of grade C2530 was used, and the samples of the slabs are reinforced with special cages, which includes the upper M1 and lower M2 plane meshes, position 1 and 2, and embedded supporting structure in the form of steel clip with vertical cages welded to it. The reinforcing bars of diameter 14 and steel grade A500C were used as principal reinforcement for the top mesh. The characteristic of concrete and reinforcing steel used for manufacturing the plate samples were provided by the manufacturer. After the producing of test samples, strain gauges with base of 20 mm and 50 mm respectively were pasted on the reinforcing bars and the concrete surface in the zones of the possible destruction of the plates. Control tests of full-scale samples of overcolumnate plates were carried out on a specially designed stand according to the developed scheme. The testing scheme was adapted in such a way that it allowed implementing the design destructive scheme, which is realized in the composition of a flat plate floor system. A stand with hydraulic jack was used to load the experimental samples, and the also watch-type deflection gauges were used for checking the deflections. The test of 3 identical overcolumnate plates were carried out to an external load values of 320, 360, and 400 kilonewtons. These values of load made up about 55, 60, and 70% of the design destructive load calculated by the yield line method. During the experimental test, the dependence of deflection on the magnitude of external load was studied, and this can be seen from the graphs up to the load value of 60 kilonewtons. Deflections of the plates grew much more slowly than after this level, which is explained by the influence of concrete work in the tensile zone, and the specified load levels can serve as moment of crack formation in the tensile zone of the plates. The maximum measured deflections of plates were 15.6 to 18.4 millimeters. The strains of concrete and reinforcement were measured on 1/4 quarter of the plate, and the regularity of the distribution of deformation can be traced on the graphs. From the very beginning of loading, the maximum strains were observed in the diagonal section 3-3, and with future loading, these strains increased, and difference between them and strains in the sections 1-1 and 2-2 became enlarged considerably. As it can be seen from the graphs, the maximum values of strains in the sections 1-1 and 2-2 were about 3 to 10% of yield point strains. Therefore, it is possible to say about the savings reserves of these bars. Examining the graphs, it may be also concluded that with the gradual approach to the supporting opening, the strains of the bars in tensile zone increased slightly. At the same time, in the section 3-3, we can observe significant increase in the strains with approaching to the supporting opening. Therefore, it can be predicted that the destruction of the plate will begin when the yield point is reached first in the reinforcing bars that pass around of the plate opening. The maximum value of tensile strains in principal reinforcement in the section 3-3 were 60–70% of yield strains, and the minimum values were about 30–40%. The strains of concrete located in compressed zone also studied. The maximum values of the concrete compressive strains were observed at the location which transfers to the section 1-1, 2-2, and 3-3. And those values were about 20–30% of ultimate values of compressive strains of concrete grade C2530. Maximum values in the longitudinal direction were about 3–8%. Examining the fields of strains distribution, it can be concluded that with gradual approach to the supporting opening, the values of concrete strains in direction transfers to the section increase significantly. At the same time, in the longitudinal direction, this tendency is much less pronounced. Fields of reinforcement strains distribution illustrate that the over-columnate plate has the largest values of strains in tensile reinforcement in diagonal direction. At the time of failure, yield lines will form along the diagonals of the plate, and the yield phenomenon, which begins in the most stressed places of the plate around the supporting opening, with the load increasing, will spread to entire reinforcement along its diagonals, forming lines along which the bending moment reaches the maximum value. At the same time, the plate will be divided into separate discs connected by these diagonal yield lines. As a result of conducting experimental tests of full-scale samples of the overcolumnate plate, the following conclusions are established. The main of them is that in this investigation, it has been experimentally confirmed that the overcolumnate plate under the ultimate load is divided into 4 discs due to formation of diagonal yield lines, and this corresponds to the fracture pattern of the plate obtained by yield line method, using of which is approved in this study. Thank you for your attention.